Hello students, in this video we'll discuss flow integrals over a curve. If we're given a curve, and I'm going to put my curve into arc length parameter from the start, r of s is equal to what? R of s is f of s I hat plus g of s, j hat plus h of s, k hat. So my curve here is an arc length parameter. It doesn't need to be. It could be a standard parameter too, or a general parameter. Here s goes between a and b. Then define the flow integral, the flow of a vector field v, of x, y, z over c by this formula. I write the integral over c of v dot t hat ds is the flow. This integral over here is the flow of the vector field over the curve. And how do I evaluate this? I integrate this from a to b. And then what? And then I plug in into my vector field, I input the curve. So I input the curve into my vector field. What do we know about t hat? We know that t hat is exactly just the derivative of the curve in arc length parameter, right? So this will be just dr ds, and then times ds. Well, we can also equally well write this. The ds's in some sense cancel here, and you can just write this as the integral from a to b of v of r of s dot dr, right? So any of these three expressions represent the flow of a vector field over a curve, right? And so let's make some sense of this. So I'm really doing the average value of v dot t hat on this curve. So if we have a vector field, here's y, and let's do y and x for a two-dimensional example. If my vector field looks like this, there's my vector field. Let's say it does something like this. So it's pretty clear what the streamlines of this vector field are going to look like. Maybe we can't compute them exactly. We may not be able to compute the exact streamlines of this vector field. But if I was to draw a curve like this, let's do something extreme. Let me draw this curve over here. Well, I've intentionally tried to draw this curve, so when I draw the tangent vectors to this curve, it looks like the tangent vectors to this curve all make 90-degree angles with respect to the vector field. I've tried to make that the case, right? And we know that in this case, v, the vector field, and t hat, these vectors over here, are perpendicular to each other. So when vectors are perpendicular, that product is 0. So for this curve, the flow should be 0. There should be no flow because it's the worst case scenario. All the vectors are perpendicular to the curve's tangent vectors. That's a bad situation for flow. Whereas if I gave you this vector field over here, try to draw this as best I can, like this green one. Well, this vector field now v and t hat, that's v and that's t hat, are in the same direction. So in some sense, this is going to be what? That's going to be the overall magnitude of the vector field. Well, the overall magnitude of the vector field squared is as large as this thing's going to be. So this has a large flow. So we'll put flow is large here. So these flow integrals, if the flow integral is large, it's detecting a streamline. So large flow large, means that you have a streamline. Flow being equal to 0 means you have something antithetical to a streamline. So you might call that a flux line, a line of flux. So we'll call these flux lines. That's a U, flux lines. Okay? So let's do an example of one of these flow integrals. Here's an example. Let's find the flow of the vector field v of x, y, which is x I hat plus y j hat. This is our vector field of position. Vector field of position over the unit circle. These are our classic examples. So here, we would like to compute this. So let's parameterize our unit circle, the arc length parameter of the unit circle, and it doesn't have to be the arc length parameter. This formula over here tells you that in some sense you don't need to have the arc length parameter. You can just have a general parameter and just dot the vector field v with the derivative of the curve. But we can put this one into arc length parameter, cosine of s I hat plus sine of s j hat. That's the arc length parameter for the unit circle. Of course, s here goes between 0 and 2 pi. That's my arc length parameter. And so now this flow integral becomes the integral from 0 to 2 pi. And for x, I put what? For x, I replace x with cosine of s. So I have a cosine of s I hat. And then for y, I have a sine of s. So sine of s j hat. And then I do the dot product of this with t hat. Well, t hat's going to be what? It's going to be negative sine s I hat plus cosine of s j hat. That's the derivative. And then ds. Okay? Well, now this first term of the dot product, I'll have negative sine times cosine. So I'm going to have the integral from 0 to 2 pi of negative sine s cosine s, then plus sine s times cosine s, sine s times cosine s ds. And that is just 0 because the intertime terms cancel out. So I have 0. So what does 0 say? It says that this vector field and the circle are going in exact opposite directions of each other. We can see that because the unit circle looks like what? The unit circle looks like this. That's y and that's x. So that was the curve I was given. I was given that curve. And what did our vector field do? Our vector field was radial. It was just the vector field of position. So our vector field looked like this. So our vector field is going exactly right out of the what? Right out of the unit circle. Exactly in the opposite direction of the tangent vectors. Like so. So that validates our answer that the flow of this vector field, the flow of the curve over the vector field, is equal to 0. Thank you very much.